So if it's a DC machine, you will be having permanent magnets depending upon the torque requirement. If it's for a small laboratory scale application or for student projects, we can go for PMDC motor. But if you're talking of huge industrial applications, then we need to talk of electromagnets, wherein you have everything working in the alternating domain, which would be then in the end rectified to provide the direct DC output. So the rotor circuit is the rotational element which is slotted and kept inside the machine. So the slotting is nothing but it's not a continuous structure. Rather, it has iron laminations and they are stacked one above the other and to give a shape of a cylindrical core. So this laminations is primarily to reduce the effects of eddy current losses. So that is something which all of us are aware of when it comes to losses in any machine. So you have the material based losses and you have the operational losses. So eddy current losses falls under the category of operational losses. And that again can be reduced with through the changing the structure of the core. The next one would be the circuits or the windings that are wound over it. So across the armature, that is the rotor circuit, it's nothing going to be your armature winding. So now here again, depending upon the requirement, they can be connected either in series or in parallel. And accordingly, if they're connected in series, you will have the series machine. If they're connected in parallel, you'll have the shunt machine, or it could be connected in combination to provide you the compound machine. So as I told you, the external structure or the mechanical frame in which all of these will be housed is your yoke. And that is going to be having basically two functions. One is to provide a path for the flux, magnetic flux to flow. And the second one is to provide a mechanical support to the entire structure. So when you mount the machine on a bed, what you see with your eye is your yoke. And when you open the yoke, you can see all the electrical subcomponents being connected inside. So to a layman, he sees only the outer frame. He doesn't see the electrical circuits. So if you have to see it, you have to open it and check it inside. So the poles are, again, the stator poles will be welded or will be connected to the yoke, and it is the field windings or the stator windings would be wound across the poles. So when you are winding it on the poles, it could be either in series or parallel with the armature windings, depending upon the application. And there is, again, these poles would be having something known as the pole shoe. So I can show it to you again in subsequent slides with some better picture. So the pole shoe would be mainly utilized for spreading the magnetic flux, and it is going to be responsible for the entire working flux generation and its coupling with the rotary circuit or the rotor circuit. So as I told you, the commutator is the next element, and it is very important because it can have a bidirectional effect. It can either convert the AC to DC and behave as a rectifier, or it can also be used to work as an inverter, that is to convert DC to AC. And that again will be utilized when you function this particular electrical machine as a motor. So the brushes, again, they are used to collect the signals in a safe manner from the rotary circuit and provide the same to the external load. So that is accordingly, you need to make sure that the element that is used for the construction of the brushes are carefully chosen. So usually it's either through carbon or its alloy will be used to make the brushes, because they have high electrical and material properties which can be made use of, especially when it comes to high rating applications. So we have seen how it works. We have seen what constitutes a DC generator. So now when it works, as I've told you in the beginning itself, 100% of the input need not or cannot be translated to the output unless it is an ideal condition. And we all know that our world is not an ideal condition in any aspect. So When it comes to electrical engineering concepts also, all the textbooks that we learn, to simplify our understanding, we first talk of the ideal scenario, and then in our laboratory courses we find out that in practice the graphs they vary from the ideal scenario, and then we try to see what is the variation and how much is the variation, and from there we try to understand the various characteristics. So over here, what are the losses in a DC generator? It could be the core losses, or it could be the copper losses. So now when it comes to core, it's something to do with the material that is used and the structure of the material. So the material that is used, again, depending upon the selection of the material, you could have either you would be having the hysteresis losses, and that again can be reduced by studying the BH curve of the material, and making sure that for the application the specified material performs to its best. The geometry of it can be altered. As I told you, instead of a solid element, you can place laminations of the same element so that the eddy current losses can be reduced. And when it comes to the copper losses, again, wherever current flows, you would be having the losses. And the main material that is used for the selection of the signal flow is copper. So we use it in the armature winding. So you have the armature losses. We use them in the field winding or the stator winding. You have the field winding losses. And then you also, if you make use of them in the brushes, you would be having the brush losses. So the DC generator, if I have to classify, as I told you again, based on the excitation, you would be having it as a separately excited or the self-excited. And as we've seen earlier, the self-excited would be either series, shunt, or compound. And compound can further be differentiated either as a cumulative compound or a differential compound, depending upon the relation between the induced flux and the working flux. So that is what this classification is all about. Now we move to the applications. So since all of us are interested in understanding where do we apply these fundas that we learn. So if you see here, right from home lighting or power generations as a microgrid or as a generator in any functions that we see. So right from there, all the way to high-end tech testing in the laboratories or in railways. Until a couple of years ago, the entire Mumbai region was working under DC traction. So the locomotives, they needed a DC input. They made use of the DC machines. And it is only after some years that they moved to an AC traction from DC. And so the DC machine was phased out and replaced with AC machines. So, but basically, wherever you need high precise speed control and easy operational conditions and a wide range of operational speeds, you would prefer DC machines. So the second part of it would be the DC motors. So many ways constructionally and the operations behind it, you can find the terms from the DC generator being brought in over here also. Just the operational principle would be tweaked a bit. So when I say the terms, the field winding, the rotor, the stator, the commutators, everything are the same, that the same terms, and they are the same circuits that we are importing from the DC generator. So as I told you, you have the first winding wound in the stator. It produces the working or the field flux, and it's known as the field winding. The second one is in the rotor, and it's known as the armature winding. So the stator is a stationary circuit and the rotor is a rotating circuit. So the armature current interacts with the working field produced by the stator current, and that interaction produces a torque. So we will be seeing how that production of torque happens. And it is this torque, when you couple it to a load, will be driving that load. So as I told you earlier, small DC motors, we can talk of PMDC motors instead of a field winding. So when you talk of PMDC motors, there is no field winding as such. The stator poles are nothing but the permanent magnet poles, the north and south, and you are not going to be exciting or energizing them with an electrical input. Rather, the permanent magnets properties will dictate the generation of the magnetic field between the poles. So just like in the generator, here also you have the commutators coming into picture, and they will be responsible for converting the input to DC to give you a AC output to the armature winding. So I've just cited the sources. So the schematic would be here. This is just the front view. I've opened the casing and I'm looking at it from the front. So if you see here, I have two pole pairs. So that is 4 poles, and that would be mechanically welded to the yoke, and the windings across the poles would be your field winding, and you would be having the pole shoe. As I told earlier, we'll be seeing it. So this is going to be a pole shoe. You have a much larger cross-sectional area to ensure that all of the magnetic flux from the stator gets linked onto the rotor circuit. Then you have smaller poles between the main poles, known as your interpoles, across which again there will be windings wound, and their aim is to ensure that you have the armature current and the magnetomotive force, they maintain a proportional relationship. So it's electrical circuit I have just again shown you here. So as the loop, again, it's a single turn circuit. So as the loop rotates, so depending upon the input, I have my battery or a DC power supply, which will be energizing my circuit. And because of the existence of the working field between the poles of a permanent magnet, you have the development of the torque. How the torque is developed, I'll show it to you in the subsequent slide. So again, just like in a DC generator, we spoke about Fleming's right-hand rule. When it comes to DC motor, we need to know about Fleming's left-hand rule. So here it states that the developed magnetic force would be acting in a direction that is perpendicular to the current direction of the current flowing in the wire or a conductor, as well as the prevailing magnetic field. So this is your circuit, and now you need to see how the Fleming's left-hand rule can be employed here. So as a prerequisite to the torque generation, first we need to know how the force is generated. And when you multiply force with the distance from the axis, only then you would be getting the expression for torque. So first we need to know how force is created. And again, we need to go back to our electromagnetics and revise something known as the Lorentz force. So what is a Lorentz force? We'll just see. It is nothing but a current carrying element moving in a field, working field B, would be experiencing a force F equal to B cross I cross L newtons. It's a vector quantity. And if it is going to be a single 1 meter length of conductor, you can say L is equal to 1. Otherwise, it's going to be proportional to the length of the conductor. So when we spoke about the Lorentz force in electromagnetics, we start off with the current element where we say it's IDL. And from there, we find the expressions and then we extrapolate it to a 1 meter length of the conductor. So if you bring that same Lorentz force into picture here, you can say that as per the Fleming's left-hand rule, you just need to extend the index, the middle fingers, as well as the thumb of our left hand in a perpendicular direction, such that the middle finger points in the direction of the current in the conductor, the index finger points in the direction of the magnetic field, that is north to south pole. Then obviously the thumb that would be outstretched in a direction perpendicular to both the earlier fingers, it would be indicating the direction of the created mechanical force. So that is pictorially depicted over here. So now this force, when you multiply it with the distance from the axis of interest, you get the development of the torque. So that is explained. I've just gotten a little bit into the math over here because it is absolutely essential. Else I would have spoken about it from a superficial manner here also. So here, deriving some of the concepts from the electromagnetics, I'm just bringing them over here. So I have a small charge dq of dq coulombs moving with a velocity v meter per second in a combined system. having certain electric field intensity and magnetic field intensity. So Lorentz force dictates that the force experienced by that small test charge would be dF, would be dq cross E plus B cross B. So now when it comes to a motor, I don't have E. So now my equation further simplifies because there's no electric field over there. So I can say E is going to be 0. So in such case, it's going to be nothing but dq cross B, nothing but a triple cross product. And now I can say that my V, which is my velocity, is going to be nothing but rate of change of displacement. And that displacement would be along the length of the conductor. So where the lengths cut out or get added, you get the variations in the velocity. So that is going to be dq cross dl by dt cross b. And I can just open up the brackets and say that the end result, I'm just playing with the terms. I can say df would be idl b sine theta. So since they're cross product, you know that if they're mutually perpendicular, the effect would be the maximum because theta would be 90 and sine 90 is 1. But for all of the angles, there would be some value of theta. So sine of that value would be contributing to the overall force development, which would be less when you compare it with the df where all the elements were mutually perpendicular to each other. So that is shown in this particular figure, wherein the effect of theta can be understood from it. So if I need to extend the same concept for the entire length of the conductor, I simply integrate it. It's a definite integral. So I'll get the expression as BIL sine theta, and that would be the expression for the developed force. And now it is that force which would be responsible for the movement of the loop. And if you see now here, at the first instance, theta is at 90 degrees. And now the force would be acting on the armature conductor and in a direction dictated by the Fleming's left-hand rule. So I can see the conductor now beginning to rotate. So on the left conductor, it would be F equal to BIL. And since it is a symmetric circuit, I would be expecting the same magnitude of force to be acting on the right conductor, but again, by Fleming's left-hand rule in a direction opposite to that generated in the left side. So because of which I have the negative sign. Have the distance between the two paths is of W meters. So you can, I'm not shown it in the picture, but it is pretty clear that the left side and the right side circuit, I have the separation distance to be W meters. So when the armature will turn by certain angle alpha, so that is shown over here, I will get the development of the force and is W meters because the two circuits are separated by that much of distance. So I have F cos alpha, which is going to be the tangential component multiplied by W. So this alpha contributes a lot to the development of the torque. And in such cases, when alpha is 0, that means when there is going to be an alignment in the axis, you get cos of 0 to be the maximum value. So in such case, the torque generated would be maximum. So I've just elaborated the same diagram here. So for different values of alpha, I'll be showing you what would be the torque generated. So here there's, again, as I told you, there's an alpha. So as the term alpha decreases, so the value of torque also will be varying. And now for a given value of alpha, you will have tau equal to BIL W cos alpha, which is less than that of when alpha was 0, which would be BIL. So you can see now how the values will be changing for different positions of the circuit. So just like what we spoke for DC generator, we have the same explanations for the components of a DC motor when it comes to the mechanical components as well as the electrical components. So the mechanical component would be the shaft, the commutator, the interpoles, the yoke or the frame, as well as the poles. And the electrical components would be the windings in the poles or across the rotor. So their interactions would be giving you the rotational action, which can be coupled via the shaft to the load. So since we have already explained it earlier, I'm just showing the main points to you. And the explanations are the same as that it was for the DC generator, including that of the commutator and the brushes. Again, here the losses involved would be broadly classified as core losses or the iron losses, the mechanical losses, the stray load losses, and the copper losses. So as electrical engineers, we would be concerned with the core losses and the copper losses, because stray load losses is out of our control because it all depends upon the load. And the mechanical losses is something to do with the mechanical coupling of the motor with the load, which again we have limited scope to improve. But the copper losses and the core losses we can definitely improve by suitably altering our designs and winding designs as well. So the DC motors, again, just like in DC generator, depending upon how you excite the windings, you can be classified broadly as separately or self-excited. And under self-excited, just like in the case of DC generators, we can say whether it is a series wound, a shunt wound, or a compound wound. So where do we apply it? Again, depending upon the arrangement of the windings. If the field and armature windings are in parallel, it's going to be a shunt DC motor. So in such a case, the basic characteristics is that you get a constant speed operations, and you can use that in certain applications like reciprocating pumps, centrifugal pumps, lathe machines in mechanical workshops, then blowers and fans, drilling machines, milling machines, machine tools. So anything in a mechanical workshop can be achieved with the employment of shunt DC motors. Your conveyor belts, if you've seen them, they rotate at a constant speed. Then your weaving machines, spinning machines, etc. And something with higher torque characteristics and variable speed, if you require, then you need to move on from a shunt system to a series system. So again, high speed conveyors, elevators or hoists, cranes, electric locomotives that draw huge loads. So you can see in the current electric locomotives that India is producing indigenously, of course, with the help of France, electric locomotives. So again, when it comes to combinations, you can talk of compound motors in shears or heavy planers, rolling mills, elevators, etc. And to design all of these, first we need to talk of the software that we use, because it is not practically possible to design anything in real time and then change it again and again if there's a mistake. So to make sure that that is not happening, we first design and do the entire mathematical modeling and analysis in a simulation platform. And once that is satisfactory and validated by the experts, only then we transport it into real time. So the most familiar software for all of us in the academic and student fraternity, it would be MATLAB or Simulink. But there are also other dedicated softwares like COMSOL Multiphysics, SimScale, etc. And if you want to talk about magnetic field analysis and all, then you can talk of Maxwell 2D, etc. So there are those kind of softwares also. Then there's ANSYS, which can be utilized for design and analysis of machines, especially the structural toolbox of it. So there are a lot of software platforms which can be utilized, and it's good for furthering even the research in the area of electrical machine. So coming towards the end, I'll just show you a small demo of the DC generator. So you can see here, the load is a lamp load, and it will be driven by a motor, which will be coupled through with a generator. So I'll just show it to you once again. So this is just a simple demo of a DC generator. So if you see here, I've taken from YouTube video. So the load that is going to be used would be a lamp load, and it would be coupled. We'll have a motor and a generator, which would be coupled, and the motor would be driving the generator to light up the particular lamp. And you would be having a certain other passive components like capacitors to smoothen out the signals. But that again is not the point of interest in this particular talk. So here what they are doing is he's just focusing on its construction aspects. And I'll just show it to you the end, how it looks like. So the two shafts of the motor generator set would be linked with a rubber band, and that would be responsible. So I'll just show it to you towards, I'll take you to the end. So you can see the driver circuit and the generator circuit, they will be coupled through a wheel, and you have the rubber band which would be acting as a coupling member. So once you start the motor or the prime mover, when it starts rotating, obviously the generator circuit would be ensuring that there's an electrical output. And since you're connecting the electrical output across to a lamp, you'll get the flowing of the charge and you'll get the glowing of the lamp. So you can see that over here. So I'll just pause for a second to show it to you. So the initial energization to the prime mover is given by an electrical DC input. And once the motor then starts rotating, it is back-to-back effect. So the rotation of the motor will be responsible for the generation of electrical output because of the operation of the generator. And then you have the lighting of the bulb. So that is a simple student project demo of a motor generator set to generate an electrical output to light up a lamp. And this can be used for small scale applications like lighting up a lamp, powering up your mobiles, etc. So for a DC motor, you would be having something similar. Coil. So you have a coil. Here it's not a single turn coil. You will have n number of turns that will be kept within the acting circuit, and you have your magnets also brought in over here. So as the magnet, so the variations in the flux is brought in by the movement of the magnet. So you will be having the magnetic field that will be interacting and creating the force and hence the subsequent torque, which would be responsible for the rotation of this particular coil. So I'll just show it to you over here. So as the force gets developed, you can see that there will be a force multiplied by the torque. So you can see as soon as the magnet is brought in its vicinity, you will get the rotation of the circuit. And this will be dependent upon the positions of the magnet. So as you pull out the magnet, you will see a different speed of rotation. As you bring in the magnet, again, you will see another different speed of rotation. So you can either make use, so that is going to be the inside aspect of it, and the outer aspect of it, wherein the energization is done, that would be with the help of a electrical input. So you can see, for since the magnet is now kept outside, you will see different characteristics of rotation as what was opposed to what was seen earlier. Now bring it much closer to the circuit, you will see another characteristics of the rotation. So you can see the speed of rotation is going to be slightly more faster. And you bringing it much more closer to the working area, you can see the speed of rotation will increase. So I hope, so that is a map of electromagnetics. If you understand, then you will be able to appreciate the beauty of the physics over here. So moving on. So coming to the most important aspect for all of us over here, what are the career opportunities? So to build a strong fundamental career, you need to know how to work with the different machines. For that, you need to know what are the types of machines, how do they work, and how are they designed, if it is being done by someone else. And if you are doing the design, then you need to know the types, its working, the objective, and for what application it is going to be employed. So once all of these aspects are understood clearly, then it's just a matter of understanding how to develop the design in a software platform, testing it, getting it validated before sending it for fabrication. So once that is done, your machine is ready and you can again validate it in real time. And once it is successful, you can then send it for mass production. So it's a highly rewarding career if you're talking of it from a production point of view. Or if you're talking of it from an applications engineer's point of view, wherein you are just going to be using the machines in the available in the market, again, in such a scenario, you need to know the types, the working of each machines, and how to analyze its working and characteristics. Then you can be a very successful electrical machines expert, and you have different spheres of the core engineering disciplines waiting to employ you. So some of the active sectors I have just shown you here: railways, shipping, aerospace, defense, heavy industries, power plants, automobiles. Since we talk of everything as electric vehicles, you need to know about DC machines over there as well. Okay, so they play a huge role in conventional, hybrid, as well as electric vehicles. So these are just some of the most active sectors wherein electrical machines specialists find a huge demand. There are many more, which we can discuss at a later point of time. So with that, I end my talk, and I thank you for your patient hearing.